Have you wondered where the formulae on the physics information sheet comes from? Do you even trust using those formulae? In today's video, I will be deriving the equations of motion. In order to do that, consider an object at the initial position xi with a velocity vi when the time is ti. Now, to demonstrate this on a diagram, I will choose a reference frame where I say that I have my x this side and my y axis. I'll choose to work with the x-axis. So that means that I'll say my motion is occurring along the x-axis, along a line that is parallel to the x-axis on my frame of reference. Now, on this horizontal line, we will have the starting point here, which is 0 meters. We call this the reference point, meaning that's where we start measuring our position or displacement. This is 0 meters where we start doing our measurements for the position. Now, on the statement that I've set at the top, it would mean that my initial position xi, right, would be somewhere here. I know that it is somewhere here because I'm not starting at 0, 0. I'm starting at some position xi, meaning from here to here I'll have a vector given by the arrow that I've drawn here. So this position is represented by this vector here. So this position could be 5 meters away from the reference point, for instance. Now, this is to say that if I were to draw this object that I'm referring to, it will really be somewhere here. Further to that, on my statement, I've said that at this position here, the object has an initial velocity that is given by this vector here, vi. And this occurs at some initial time ti, meaning if we were to look at our clock reading, we would have the initial time ti. We start measuring the motion at this position to be ti. Now, because this object has a velocity that I've chosen to be in this direction, it means it will continue moving in this direction towards the right. Now, I'm going to then put in some more information to describe that motion that goes to the right, to say that the object moves on a straight line with a constant acceleration. And I'll call that acceleration A, until some time tf at the final position xf, right? So what have I said here? I'm saying that the object will continue moving towards that direction because we can see we have this velocity. But this motion would be such that we have a constant acceleration. I'm assuming here, or I'm choosing my acceleration to be constant. So this means that the acceleration doesn't change as the object moves towards the right. Meaning when the object is somewhere here, well, before we go there, at the start position here, our acceleration would be a. Let's say we said it's a, right? We said our acceleration should be a. Now, when the object gets to some point here, the acceleration will still be a because it is constant, it does not change. When the object is somewhere here, we will still have our acceleration at this point to be a value a again, right? And let's say the object continues to be at this point again, the acceleration would still be a constant. It will remain unchanged. It is a uniform acceleration. It will still be a. Now, this means now that our object, let's say it ends somewhere here because I don't have space, which we'll call this the final position, right? Is the final position that it reaches. This final position, you have to take note that it is measured from the origin, meaning it will be a vector that starts from 0, 0 up until this point here. Right, it's a vector that moves from 0 up to this point. So this could be something like 10 meters away from the reference point. This is where our object is now located. This is the position of the object. That's where it is now located in space, right? Now you have to then understand that the object was displaced from xi to xf. That means that it actually covered this length here in that direction. So this means here that the displacement will be from xi to xf. This is the change in x of the object, right? So that means it will be given by x final minus x initial. Now let's look at this very carefully. What I'm saying here, I'm saying that from this whole length here, which is x final, I'm subtracting this length here, which is x initial. I'm removing this. I'm subtracting it. I'm saying x final minus x initial here. Then that will give me the length from here to here, and it's a vector that goes in that direction, right? Now, the other thing that we have to take note is that this very displacement that I'm describing here, right, when we check the clock reading, when the object is at this position, when it has covered this displacement, we will see that we'll have some time tf when you look at your timer or your clock, right? So that means the length of time or the duration from this initial position xi to the final position xf will be given by the change in t is equals to t final minus t initial. Remember that in physics, every time we use this symbol, the change in t, or what we call delta, we always subtract final from initial. So to get the time, I'll say this later time minus the time that we started at. It should give me the length of time or the duration that it took for the object to be displaced from the initial position xi to the final position xf. Now at this stage, one may be interested to then know that the object will have some final velocity here, vf. What is that final velocity? One might want to know that. In order to then determine that velocity, I'm going to use the definition of average acceleration. I'm going to argue that from the definition of average acceleration. We know that the average acceleration, which is given by avg, right? So this means average acceleration is defined as the change in velocity over the total time that it takes to change that velocity. So we're saying here, because I can see that my velocity will change from vi to vf, if I find the difference between the two, v final minus vf, and divide by the total time, that will give me the average acceleration that the object has as it moves along that straight path. But remember that if you have a sample data, the average acceleration, or the average of that sample data, can be defined as the sum of the data points divided by the total number of the data points. How do I mean? I mean that I have my data points here of acceleration at this point, acceleration when the object is here, acceleration when the object is here, and acceleration when the object is here. If I add all these accelerations, right, I'm taking them as if they are data points, and I divide by the total number of data points, which is going to be 1, 2, 3, and 4, I should get the average acceleration. So if I were to write this mathematically, it will be something like a plus a plus a plus a divided by 4, because I have 4 data points. But remember that this is still the same as the final velocity minus the initial velocity over change in time. So I'm just rewriting this as v final minus v initial, and I'm keeping the time as it is. Now from here, deriving the formula for the final velocity becomes very, 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 very boring, because I'm going to add all these accelerations here, so that I'm going to have 4a, because a plus a is 2a plus a is 3a plus a is 4a, and then here I'm having a 4a divided by 4a, and this is equals to v final minus v initial over change in t. Notice that the 4 and the 4 cancel each other, so that I'm left with a is equals to v final minus v initial over change in t. Now I'm going to cross multiply the change in t with the a, and I'm left with a times change in t is equals to v final minus v initial. At this stage, I'm going to transpose the v initial to this side, so that it becomes a plus vi. Now I'm only left with v final is equals to, now I'm going to have the vi, because it will be positive when it comes to this side, but I still have here the acceleration times change in time. This I will call equation 1. This is our first equation of motion on the information sheet of our physics question paper or books that we use in physics. And I have to emphasize at this point that this equation becomes true if and only if the acceleration is constant. Because remember, if the acceleration was not constant, if it was not the same throughout as we move like that, we wouldn't have this part here to be a here, and this equation wouldn't look like the way it is now. So this equation is only valid, or it can only be used when the acceleration is constant. This formula is extremely powerful. It allows us to calculate any object's velocity at any time, provided that we know the initial velocity and the constant acceleration.